All right, this is the Geometry Unit 9 Lesson 4 video over triangle proportionality. This is going to be a weird video. There's really not much here that isn't a proof, so I'm going to work through these proofs for you guys, but also there are 3 questions down at the bottom where you need to know these theorems that are in these boxes as you go through. But the triangle proportionality theorem basically says that if a parallel line cuts through a triangle, like parallel to one of the other sides, then it cuts those sides proportionally. So in other words, with this example, the relationship between these sides and the relationship between, as they relate to these sides, would be the same relationship. So they're proportional, which you should know what that means based on what we've been talking about up to this point in the other lessons. And so then they go into a proof. So we're going to go through and just do the proof together. So you guys have everything you need for this because you're not going to be responsible for the proofs on the test. So it says that we have BE is parallel to CD. So this is parallel to this. That's our given. And we want to prove that these sides are proportional. Okay, that's what we're saying right here. So it says here, first of all, that angle 1 is congruent to angle 2. And angle 3 is congruent to angle 4. So this is congruent to this. And let's pick another color. Let's go a little green. This is congruent to this. Okay, how do we know that? Well, we know that because that is a transversal. And so then those are corresponding angles. So let's look through our answer choices. And we see those are corresponding angles. So then, because of that, we can see that those triangles are similar. How are we proving that? Well, which theorem would it be? It's going to be the theorem that we have angle, side, angle. Or sorry, angle, not angle, side, angle, angle, angle. We don't need a side because similarity, you just need 2 angles. So we have that these are congruent, or sorry, similar triangles. So because of that, we know that the sides of this triangle are proportional to each other. And we know that based on the segment addition postulate, that the different parts of these add up to make that whole thing. In other words, AC is made up of AB and BC. And then similarly, AD is made up of AE and ED. All right. And then basically what they're doing is they're doing some substitution from number 5 and combining number 4 and number 5 to make the statement in number 6. And so that's going to be substitution. And then they basically do some more arithmetic to get down to the fact that BC over AB equals ED over AE. Again, don't worry too much about this proof. Focus on knowing the theorem definitions. And so let's go ahead and jump down. We get the converse. Converse basically says if the sides are divided proportionally, then the line is parallel. So it's the opposite. And so we'll have another proof here. Not too long. So now we say, okay, we have this triangle, and AB and BC is proportional in the same way that AE and ED is. Okay, and so we want to prove that the lines are parallel. Well, first things first, angle A is proportional to itself, or sorry, congruent to itself. That's the reflexive property. You should know that one. Anytime in geometry we say something is congruent to itself, that's the reflexive property. And then because of that, we can prove the side angle side similarity theorem. And so what triangles are we talking about here? We're talking about ABE and ACD. Not too challenging to see. That's the only answer that corresponds with anything about similarity. So that's going to be answer choice C. And then because of that, we know that ABE is congruent to ACD. The angle ABE, that's this angle here, is congruent to ACD because those are the definition of corresponding angles, or no, the definition of similar triangles, actually, is where that comes from. Because these are similar triangles, these angles must be the same. All similar triangles have the same measures of the angles. And then the converse of the corresponding angle theorem tells us that we have parallel lines, because we know that if this is these are corresponding angles here between these two lines, therefore those lines have to be parallel based on the corresponding angles theorem. All right, make sure you get those answers down. And then we'll move on to the corollary one, which says that if you have 3 or more parallel lines with 2 transversals, they divide the transversals proportionally. In other words, this makes proportional triangles and proportional shapes as this transversal line goes through the diagram. And then this one says if one transversal intersects 3 or more parallel lines, so that it's divided into congruent segments, then any transversal that intersects the same parallel lines will also be divided into congruent segments. All right, let's look through these other proofs. Honestly, this isn't really presented in the most interesting way, so we're just going to kind of slog through this. We have 3 parallel lines. We have angle AB, or side. We have AB, CD, and EF all parallel. And then we want to prove that the following are proportional. We're going to prove that AC, BD, and CE, DF are proportional. So we've got to prove that they have the same relationship with one another. So we've drawn a auxiliary line, EB. We've drawn this line through the middle here, the diagonal line right here. And then we've said, okay, AC over CE is congruent to BG over GE. We're using the triangle proportionality theorem. And then we're using the same theorem for the next statement, the triangle proportionality theorem. And then finally, AC over CE is equal to BD. So all we've done here is we've done some substitution. We've taken this and we've replaced it in this statement. So we've replaced it in the statement for this BG over GE. So we are taking this out and we're replacing it with AC, and that's going to be this substitution or transitive property of similarity. All right. Another proof, last one. We have BC is parallel to DE and FG. And we have that BD is congruent to DF. So we have BD is congruent to DF. That's a given. Then we convert that into an equality statement. So that's going to be the definition of congruent segments right there. That's going to be answer choice E. And then we begin to, we do some algebra. We're going to do the division property of equality because we're dividing both sides of the equation by df. So that's where this is coming from. We're divide by df. And so that's going to be the division property of equality, which is answer choice C. df divided by df is 1. That's just simplifying. And then we have our other given, the fact that those lines are parallel. BD over DF is congruent to CE over EG. That's just saying that because these are triangles, that's going to be the converse, the corollary one of the triangle congruent or proportionality theorem. So it's choice B. We know that BD over DF is 1. Then we multiply EG, or we multiply both sides times itself. So we get this little statement here. We do the inverse, and then EG over EG equals 1. EG over EG, or then we're doing we're substituting from line 7 right here. We're taking this 1 and we're substituting it for CE over EG. We multiply both sides times EG. That's going to be the symmetric property of equality. Nope. That's going to be the, feels like there's one missing here. We'll call it the transitive property. No. Interesting. We'll call it equal lengths for H. Not sure about that one, to be completely honest, everybody, but that's okay. There seems to be a missing one. It should be the multiplication property of equality. It's not there, though. But then this is definitely the symmetric property, because basically what we've done is we've switched the sides of the equal sign. That's going to be the symmetric property of equality. Again, I'm not worried about these proofs. Do not sweat the proofs. Any proofs that appear on a practice test, quiz, or test will be thrown out. Jumping down, you need to match the theorem or corollary with the statement you see here for 5, 6, and 7, 5, 6, 7, and 8. Those are all coming from the lesson. Those are going to be these boxes on the screen here. So match up the theorem with its definition. And that is it for lesson 4.